Okay, let's look at another situation very similar to the previous one. Okay, so instead of the object being dropped from a hill, in this one, let's say we have a loop, and a loop of say radius r, but the object now is being released by a spring. Okay, so we have a spring constant k. We have a block that compresses the spring by some amount. Our goal is to figure out the amount x that we need to compress it by. So how much is x such that it completes the loop? Okay, so we'll use the same idea as from the previous problem. First thing is we'll figure out the speed, the condition. Okay, figure v at the top, and once we know v at the top, then we can use energy conservation to do the rest of the stuff. Okay, so we're going to assume everything is frictionless in this problem. Okay, if there was friction, then we'd have to account for friction in a certain, slightly more involved way, and we'll do that in the next example. So we have speed at the top v, we're going to figure out, and then the next thing we'll figure out is find x, the spring compression. You probably guessed it correctly. Now, to figure out the speed at the top, we need to know our condition for the motion at the top, and what we have is we have our forces. So we have a force at the top which is equal to F sub n, and then we also have mg, and the result of these is equal to mv square over r. Okay, now that we have this, let us write our equation, which is Fn plus mg equals mv square over r. Now we know that the minimum condition is that Fn become equal to 0. Okay, so this equation ends up giving us v equals square root of r times g. Very good, we have that. Now that we have this, now we are going to use our MEI equals MEF. Okay, the fact that the mechanical energy is conserved. And in the beginning, the block's not moving, so 0 kinetic. It is at its lowest point, so 0 potential. And the only thing is that the spring, our massless spring, has some spring potential energy, which is 1/2 k times x squared. X is what we're looking for in the problem. K is given. At the top, at the highest point, all we do is we know the kinetic energy, which is 1/2 m times square root rg square plus mg times 2r, and 0 for the spring potential energy, because the spring, once it releases, it's done. It doesn't do anything else anymore. Now that we have this, what we're going to do is we can now simplify this. Let's write this as 1/2 k x square equals 1/2 m times gr plus 2m gr, and as you've guessed, half plus 2 is 5/2, so it's 5/2 mgr. And now we have x, the halves cancel out. We have x squared equals 5 mgr over k, which implies that x is equal to square root of 5 mgr over k. Okay, so this is how we obtain the spring, the amount that the spring has to be compressed by. So in the next video, what we'll do is we'll introduce friction, and then we'll look at a situation where now, in addition to the spring or any other forces that we may have, we also have to deal with friction, and how do we go about doing that.